All right, so let's work this problem. A little different than the last one. You'll notice that, again, we have a continuous load, so that means we can write a continuous moment. So with direct integration, we can get a continuous expression for displacement and slope. So just like in the previous problem, I'm going to find my reactions first. So I'll call this the reaction at A, and then go over here at B, find the reaction at B. To ease my calculations, I'm going to find the concentrated equivalent force for this distributed loading. This load is triangular shaped, so we know the area of a triangle. It's 1/2 base times height. So that should be WL over 2. And let's say, what's the distance from B? It would be the length, a third of the length. So that would be L over 3. Also, as we move forward, what kind of conditions do we know about slope and displacement? Unlike the last problem, I don't know where the slope's going to be 0. It's going to be 0 in here somewhere, but I have no idea. But I do know that my displacement at x equals 0 is 0. And my displacement at x equal L is 0. So there's my two conditions that I'll use. Also, I'll plan ahead a bit, and I'll say, well, I'm going to cut my structure to find the internal moment, and I'm going to look at some distance x. Do you want to look at the left side or the right side? Yeah, I think the left is a much better choice. It's just a triangular load, whereas the right side is trapezoidal. So we'll go left. So since we're going left, we're going to need to know the reaction at A. To find the reaction at A, I'll sum moments about B. So let's do that first. So using right-hand rule for my sign convention, I will sum moments at B and make sure the system is in equilibrium. So let's do that. I'm going to start here at B. The concentrated equivalent force creates what kind of moment about B? Positive or negative? Positive. So the force is WL over 2 with a moment arm of L over 3. And then the reaction at A creates negative moment with a moment arm of L. So my reaction at A is WL over 6. So now I'll come down here and we'll draw a free body diagram of this cut. I just found my reaction at A. It's up, and we found that that was WL over 6. At the cut, we're going to assume we have a positive shear and a positive bending moment. And then we have a triangular load. What is the value of the triangular load there for an arbitrary distance x? Well, that means I have to write an equation for the load. The load is a straight line. It starts at 0, so I know the y-intercept is 0. And then what's the slope of this line? W, height, over run, L. Rise over run, right? So that means that this should be Wx over L. And you can check it. When x is 0, what do you should have? You should have 0. And when x is equal to L, what should it be? W. So that equation matches both. Sorry, I don't know why it's blinking. It matches both at A and B. So I know my equation is good. So the first thing I want to do is find the concentrated equivalent force. I'm going to run out of space in there, so I'll just call it F1. And then also it'll be a distance from the cut D1. So what's F1 equal to? Well, it's a triangle, so it should be 1/2 base times height. So 1/2 base x times height Wx over L. So that's 1/2 space times, oops, that's a W. So that gives me WX squared over 2L. And that you can check too, right? When the length is 0, you have no force. When the length is L, you should have WL over 2. When you put in L there, you get WL over 2. So it seems to work. And we know the distance D1 is the distance divided by 3, which would be x over 3. So now I'm going to find my internal moment. So I'll come over here and I will sum moments at the cut. So starting at the cut, I have the internal moment, which in my sign convention is positive. About the cut, F1 creates positive moment. The force is WX squared over 2L, and the moment arm is x over 3. And all the way over here on the left is this force WL over 6 times the moment arm of x, and that creates negative. So I have WL over 6 times x. So therefore my moment, just throw everything to the other side of the equation. Looks like there's a W. Let's see, can I get clever here? I can pull out, oh, look at that. There's a 6 there and a 6 there. See that? So I'll pull out W, and I'll pull out a 6, and I think I'll even pull out an L. So in the first one, that'll leave me with, what, x cubed? And in the second one, it'll leave me with L squared x. Does that look right?
How did you get the L squared?
Well, I pulled an L out. So if I pull one out in the denominator, I have to add one to the numerator. Right? Because L squared divided by L is L. Is that right? I'm just trying to get some stuff I don't need out of there. So I have a much simpler polynomial to do my integrations with. Does it work? Is this right? Well, hopefully the moment at x equals 0 should be 0. So I put x equals 0, and that's right. And then over here at L, I should also get what? 0. So the moment at x equal L should also be 0. And if you put in L, what do you get? 0. Yay! So I'm feeling pretty good that maybe this equation is a good one. So now what do we do? Direct integration. So we know that our slope is going to be the integral of the moment divided by EI. In our case, E and I are constants, so we'll factor those out. We'll pile them in with this other piece here. So I'll have W over 6 EIL. And then the integral of what's left over, which is minus x cubed plus L squared x times dx. So if we go ahead and do that, I've got W over 6 EIL. And then integrate this, I get minus x to the 4th over 4 plus L squared x squared over 2 plus I generate an integration constant. And again, I don't know anything about slope right now, so I have to let this C1 just sit there. So let's integrate that and get displacement. So I know displacement's the integral of slope. So I just integrate this guy. So again, I have the same constant sitting out there, 6EIL. Integrate this guy, I get x to the 5th over 20 plus L squared x cubed over 6 plus C1 x, and then a new integration constant, C2. So now I can go back up here and get my boundary conditions where I know that the displacement has to go through these 2 points. So let's start with the easy one, x equals 0. So evaluate this function at x equals 0. It should be 0. So 0, 0, 0 looks like C2. So I know C2 is 0. That was easy. Let's do the next one. At x equal L, it should also be 0. So what do I get? Well, I've got my constant here, W over 6EIL. When I put in L here, what do I get? Well, both the numerators are L to the 5th. And I get a negative 20th and a positive 6. The only common denominator I can see to make this easy would be 60. So this would be 3/60ths and 10/60ths, right? Negative 3, positive 10. It looks like 7L5 over 60. And then you plug in L here, you get plus C1L. Everybody okay with that? Take your time. Think about it for a second. You might have to go all the way back to, I believe, the 4th grade, where you added fractions together with a common denominator. I know it's a long time. You've probably forgotten it. Did I do it right? Hopefully I did it right after all that chastising. I think it looks okay. So I can solve for C1. So C1 becomes minus 7 WL to the 4th over 360 EI, and that L cancels that L. Let's make this 3. Okay? So again, that goes in here or in here, and you'll get the final result. And for me right now, that's good enough. You don't have to spend all the time of shoving this back in here and trying to find common denominators and all that. You can, if you like. It just depends. I think when you do mastering engineering problems, it may, once you find the equation, it may ask you to evaluate it at a certain point. So you would now put in value for W, a value for L, maybe a value for E and I. It may just say E and I is constant, or maybe equal to 1. And then you put in some value for X, and you produce a numerical value. Cool, huh? You don't like it? No? I like it. It's fun. All right, so this is a good place to stop.